Cool. Hey, everyone. Good morning. Thanks for coming to my talk. My name is Jagdeep. I'm a software developer at Amazon. Today, I'll be talking about MySQL replication. Now, if you folks are wondering why am I talking about MySQL replication at a Postgres conference, the reason is like MySQL and Postgres, they have very different replication implementations. Postgres has had robust physical replication support for a long time, and logical replication was added a bit later. And I know many developers today who are working on logical replication, adding features, making improvements, things like that. MySQL, on the other side, has had like logical replication from the very early on, and that's the only kind of replication it supports. So my goal here today is to just discuss the implementation details of MySQL logical replication and hope that the folks working on Postgres logical replication can get some ideas or learn from the details. So with that, let's get started. So these are the topics I will cover today. I will first talk about the binary log, which is the replication log in MySQL. Then I will take a look at how it is used in replication. Then we will look at some GTIDs and two-phase commit, which are important for replication consistency in MySQL. Finally, we'll look at some optimization techniques, which is optimization on the source for better throughput, and also some optimizations on the replica with parallel apply. So these are the topics I'll cover today. So first, binary log in MySQL. There's a bit of a history here, right? Like why MySQL even has a binary log. So originally, when MySQL was designed, it was designed to have pluggable storage engines, which means anyone could write a storage engine. If it implements a certain interface, a user could install that storage engine as a plugin and use it. And all of those storage engines could have their own storage format or on-disk format. They could have redo logging, and some of them may not even have redo logging, so they were not even crash safe. As a result, MySQL implemented this layer of logging around the storage engine, which we call binary log. Now, this layer cannot make any assumptions about the storage engine itself or the storage format. So this log is logical, not the physical data changes, which we'll take a look in a while. And this is also the log that started being used for replication in MySQL. Things are a bit different today. InnoDB is sort of the default storage engine in MySQL. It has redo logging. It is crash safe. But binary log is still important because MySQL still uses binary log for replication. So I want to look at some of the main logs in MySQL. So today we have an InnoDB redo log, InnoDB undo log, and then the binary log. So first, the InnoDB redo log. It is the log of the storage engine. So it is very similar to write-ahead logging in Postgres. It encodes the changes to the physical data pages that the write transaction performs. So for example, if a transaction updated 3 rows and that meant changing 3 data pages, those will be logged in the redo log. And then the commit will be written to the redo log. And that's how InnoDB is crash safe. If it crashes, it can come back up and do a crash recovery using the InnoDB redo log. Since recently, the redo log in MySQL InnoDB was implemented as a circular buffer. So you have the head of the circular buffer. All the new writes from new transactions go to this head. And then you have the tail, and there's a check pointer process in the background, which is reading from the redo log, applying those changes to the data pages, and advancing the tail. Then MySQL had all this logic to make sure the head never catches up with the tail or overwrites it, right? So it was a bit complicated. But this has actually been improved recently. Just very recently, MySQL switched to similar redo logging as Postgres with write-ahead logging, which is a bunch of files on disk with increasing sequence number. That means it's not a circular buffer anymore. At runtime, a user can change the size of the redo log, and MySQL tries to keep it within that set size. So yeah, this was just a recent change in the redo log. Then we have the InnoDB undo log. It is sort of the opposite of redo log. It contains the information to undo a transaction. Now, why does MySQL need an undo log? Unlike Postgres, MySQL doesn't copy a row if you update it. It actually copies it, updates it in place, which means if you need to undo a transaction, you actually need information on how to undo it. And there are two main places where undo log is used. During crash recovery, let's say a transaction needs to be rolled back, not rolled forward. So MySQL will use the undo log. At runtime, if there's MVCC uses the undo log. For example, a query needs the older version of the row because it started a while ago. Some other transaction overwrote it. MySQL will use this undo log to generate that older version in memory. So MySQL has both undo and redo. But the thing that we are most interested in today's talk is the binary log. Binary log is similar to the redo log in the sense that it contains all the changes from the write transactions. But unlike redo log, which contains the changes to the physical data pages, it actually contains the changes in a logical format. What it means is, let's say you have a transaction that updated or inserted a bunch of rows. The binary log will actually contain the new column values for those rows. It would have no information about where those data pages live on the disk. Same for deletes. It will contain information about which row got deleted with which primary key and what are the column values. Binary log is the log that's used in replication. And it's a bit tricky because in crash recovery, MySQL has to use both the binary log and the physical redo log to perform a crash recovery. So this is just an example of a binary log. It is similar to redo log. There are some files on the disk with increasing sequence number. MySQL always creates a file on disk called binary log.index. If I cat the file, it actually has just a list of all the binary logs that the MySQL server has. As a database administrator, I can set up retention on those binary logs, so MySQL automatically deletes the old binary logs. And there are some functions I can run to delete old binary logs at runtime. And generally on the source, the MySQL server only needs the latest binary log. All the old binary logs are just used for replication. So next I want to talk about what's the two formats of writing this binary log. So originally when binary log was started, the only format was statement format. What I mean by statement format is if I ran a query, delete from blah, where, and a clause, that statement will be written to the binary log as it is, the same query text. That was the original format in MySQL binary log. But it has a lot of problems. The first problem it had was it is not deterministic. If I replay the statement, let's say it has a sysdate or any other query that can change on a different server, you will get different results. The second problem with the statement format was it also needed a lot more resources on the replica. Let's say I ran an update with the where clause, and the where clause was pretty complex, so server had to do a lot of lookups. When I'm replaying the transaction, I have to do the same work again. And the third drawback with the statement logging format was it cannot be parallelized as much as the row format. Now, so then MySQL added this row format. What row format means is instead of writing the exact query the user ran into the binary log, MySQL actually writes information about what rows changed in an encoded way where every column of the new row would be in the binary log. And we will look at some, and that solved the three problems, right? This was deterministic because it's not the query with some random functions in it. It can be parallelized easily. And also it needs less work on the replay because you can just do the primary key lookup. So let's look at these two examples, right? Here at the top, I ran a DDL. I created a table names with an ID and a first name and a last name. Then I just simply cat the latest binary log. As you can see in the output, the DDL is present as it is. So this is the statement format logging where the query is present as it is in the binary log. Even today for DDL, MySQL uses a statement format. So DDL cannot be logged as a row format because no row is changing in a DDL. This is an example of two DML examples, right? Here I inserted a name into my name into a table, and then I deleted it. Both of them changed one row each. And if I cat the latest binary log, I actually won't be able to make sense of it. I know that some values are here, but the query text is not present as it is. This is because in this case, MySQL actually encoded in a row format. But MySQL provides this utility called MySQL binlog, which I can provide with the binary log file and ask it to decode the row information. And if I use this, I can see, this is the row that my query changed. It inserted a row with my first name and last name with the primary key 1. Now, this primary key 1 was not even in the insert. It was auto-generated. But in the row format logging, MySQL will actually log all the columns that changed. And then it has a bunch of other information, right? It has information about which table changed, which database changed, and what was the server ID of the log that created this transaction, things like that. Similar example for delete. What I ran was delete star, and it updated one row. But in row logging format, MySQL actually logged the 3 column values of the row that got deleted. And this would be pretty fast on a replica if I had a big table, because the replica can just use the primary key to look up what row needs to be deleted, right? So in this way, row logging is better than statement. Other thing I want to point out is the MySQL binlog utility or decoding a binary log. It doesn't need access to a server. I can copy a binary log off the server and decode it. And the binary log itself contains all the information about what table changed, what are the new column values or row values and things like that. And that's an important thing about binary log, because to decode it, you don't need access to the source server or catalog or any system tables. It is kind of self-sufficient in that manner.
Deletion, does this work without primary keys? Like the deletion replication, or?
So if you don't have primary keys, if you look at the MySQL docs, they do say use primary keys if you're using replication, because without a primary key, the replica could be inconsistent.
So it's sort of recommended, and if you don't use it, then sometimes confusing things.
Yeah.
Basically, okay.
MySQL will have an implicit primary key, kind of like our old OIDs.
Cool. So we just looked at the binary log. Next, I want to talk about how is the binary log actually used for replication. So here I'm drawing a source and a replica. There are actually 3 important threads in MySQL replication. On the source, you have a log dump thread. Its job is to send binary logs to the replica. On the replica, we actually have 2 threads. There's an IO thread. Its job is to get the log from the source and store it locally. Then we have SQL thread, and what it does is it reads the local copy of that log, parses it, applies it to the transaction. And as it does that, it actually generates more binary logs on the replica as well. And a bit of a terminology thing, the relay log here, in MySQL, relay log means a copy of the source's binary log on the replica. So it is just another binary log, but to distinguish between the replica's own binary log and the log that it copied from the source, we call it relay log and binary log. So this is the same information, but in a sequence diagram. So on the left-hand side, we have the source log dump thread. Then we have the IO thread on the replica, and then the SQL thread on the replica. So all the source log dump thread is doing is keeping track of what are the new binary logs on the source. Then we have this sort of loop that's started by the IO thread. I call it a read loop. What IO thread is doing is talking to the source, getting the new binary logs, persisting them locally in the relay log, and doing this in a loop as long as the replication is going on. And then we have this other loop here. I call it an apply loop. So in this loop, there's a SQL thread that's reading the relay log. It's parsing the information. The information could be in a statement format or it could be in a row format, and applying it to the database. And it's also doing it in a loop as long as the replication is ongoing. And as I said, threads, so there could be multiple SQL threads if you're using parallel replication. So the the one thing that I want to talk about here is like, IO thread is getting logs from the source. SQL thread is parsing those logs and applying the transaction. How do each of them know what logs to copy over transactions to apply? For example, how does IO thread know which logs it needs from the source? And how does SQL thread know if given a transaction, it has already been applied? Should it be applied? Should it be skipped? Things like that. And that's where I want to talk about global transaction IDs.
How tunable is the feedback loop to the source server for like acknowledging everything? Or are you going to cover that later?
There is not in a usual MySQL asynchronous replication, there's not really an acknowledgement. The server doesn't know where the replica is. You have to sort of, if you want to delete the old binary logs, you just go to the server, see where the replica is, and delete things before that.
In order to track that everything made it to the target, it's like on the DBA or the monitoring system to like know that that's all applied properly.
So yeah, so if you want to see if it is applied properly, you would have to log into the target and see information about what binary logs have been applied. And then you can go delete them from the source for space management. But there's no automatic delete what has been applied or
I was more asking like if you ended up having like timeline drift because of a problem that happened or something like that. It's like on like the end users to determine that that happened, right?
I didn't get the question, but I will.
We can take it offline.
Yeah, and maybe after the presentation, I will also have some time for questions. So the thing I want to talk about is like how do the both threads know which transactions to copy and which transactions to apply or skip. This is actually done today using global transaction IDs. But even GTIDs is the new thing in MySQL. Before GTIDs, the only way you can refer to a transaction in replication is by a file name and offset. So you can say, the transaction in file name 10 offset 400, which is not a convenient way to refer to transactions. And it was actually very hard to set up replication or manage or troubleshoot replication in doing that, right? I want to talk about the few issues before GTIDs. So we were referring to transactions using just a binary log, file name, and offset. So let's say I want to set up a replica. First, what I would have to do is go to the source, take a backup, know exactly what binary log offset the source is writing to, restore the backup, and start the replication from the exact offset. As a user, I would have to enter the offset. And if I get it wrong, I may have an extra transaction or a missing transaction. And if you look at a lot of the old blogs, what they ask you to do is like pause the writes from the source, record the binary log offset, take a backup, restore the backup, unpause the writes, and use the recorded offset to start replication, which was a bit hard to get it right, and you can make a mistake, and you can have a replication inconsistency, and you may not know it for a while. The replication was also pretty hard to troubleshoot. Let's say I have an extra row or a missing row. For me to find out, which binary log inserted that row, I would have to parse through a bunch of binary logs. So troubleshooting was also tricky. Just a little bit about the circle replication. This was possible before GTIDs. So you would set up A to replicate from B and B to replicate from A, and you will ask both of them to ignore their own server IDs. So you can do it, but without GTIDs, let's say you replicate a transaction from server C. It will actually cause an infinite apply loop. Let's say B applies that transaction, it writes it to binary log, A reads it, applies it, creates its own binary log. So the transaction will get applied forever. And to solve all of these problems, to make the replication easy to set up, easy to troubleshoot, and better circular replication support for active-active, MySQL actually implemented GTIDs. So in GTIDs, every transaction is assigned a ID, and we call it globally unique ID. This GTID information is present both in the system tables and the binary log, and it is updated transactionally in the system table. And this would be an example of a GTID. There are actually two parts to it. The first part is the server UUID. The second part is the transaction number on the server, which is the increasing sequence number the server keeps. And those two things of information together, server UUID and a transaction ID, is a unique, globally unique transaction ID. So let's look at some examples of a GTID. Here at the top, I ran a DDL. I created a table. Then I ran a DML where I inserted my name into the table. And Then I can check a system table that shows, this server has 3 GTIDs. The first is the server's own UUID and 3 intervals, which actually translates to just 3 transaction IDs locally. So in this case, this was not a busy server, so I know that inserting my name was actually the 3rd transaction ID. So when I inserted my name into that table or ran that insert, what MySQL did internally was it created a new GTID, it assigned it to that transaction, and then that row and this update to the system table was actually done as part of the same transaction. So in case the server crashed and my transaction got rolled back, my name wouldn't be there and this GTID 3 would not be there. And if it commits, both of them would be there. And this is important that for MySQL to update the GTID information with the transaction data atomically for consistency. So what I showed was how the information is present in system tables and updated transactionally. Here is, I know a lot of text, so don't worry too much about it. Here I want to show that the information is also present in the binary log. So I'm just looking at the latest binary log, in this case, binary log 4, and I'm asking the MySQL bin log utility to exclude transactions 1 and 3. So I'm looking at transaction 2, which was actually the DDL I ran. So the output would be the GTID of the transaction, which is transaction number 2 from the server, and what the transaction was, which was the DDL to create the table. This is just to show that the GTID information is also present in binary log along with every transaction. Similar example, now I'm excluding transactions 1 and 2. So I'm looking at transaction number 3 in the same binary log, and the output shows, GTID with transaction ID 3 from the server is actually an insert. And that was the last insert I ran in the previous slide with my name, last name, and a primary key ID of 1. So, so we just discussed that the GTID information is present in the system tables, updated transactionally. GTID is also present in binary log for every transaction, which means starting transaction is now, replication is pretty easy. All I need to do is source auto position, and the replica would figure out exactly where to start replication from. And how it does that? It uses this logic. The transactions it need to replicate are the transaction, the GTID executed set on the source, which would be a set of transactions, similar interval like 1 to let's say 10,000. It will subtract its own local GTID executed. So what it gets is a set of transactions that have been applied on the source but not applied locally. Then the IO thread can talk to the source thread, and it can get exactly those transactions that it needs. And we saw that the binary log has transaction ID for each transaction, and the source can just send those transactions to the replica. Now the SQL thread actually also uses that information. It parses the relay logs locally. It parses every transaction. Before applying it, it will check, does this GTID exist in the system table? If not, then it will apply it. If it already exists, it means this transaction has already been applied, so it can skip it. That's why the information about system table being updated atomically with the transaction data is important for replication consistency. GTID also makes crash recovery very simple on replica. So if a replica is applying multiple transactions in parallel, even out of order, if it crashes, it can come back up, look at the system table, and know exactly what transactions got applied and what got rolled back, and reapply the ones that got rolled back. Cool. So far, we sort of looked at how GTIDs are used to automatically figure out replication position and what transactions to apply. There's still one problem that MySQL needs to solve, and that's on the source. So for the replica to be consistent with the source, on the source, binary log needs to be consistent with the InnoDB database. If both of them got out of sync, the replica won't be consistent. What I mean by that is all the right transactions on the database need to be present in the binary log. But in addition to that, binary log should not have any extra transaction than the database. If any of them are not true, then our replica would be out of sync with the source. This is a bit tricky in MySQL, right? So we know today, everyone almost uses InnoDB, which is own redo log used for crash recovery. And then we're also writing a different log for replication called binary log. Redo log is used for crash recovery of the storage engine. So how does MySQL ensure that these two are always in sync and not have extra or missing transactions? So it implements a sort of two-phase commit. And I will walk through every step, so you don't have to look at all of it. So this is sort of an overall view of MySQL's two-phase commit. So the step one is the client sending a commit to the server. So this is a client that had open write transaction, it modified a bunch of rows, and now it sent the commit to the server. So what does server do? It enters the state called prepare phase. In this state, the server will make sure all the transaction data is in the redo log. Then it will go to the redo log and mark this transaction as prepared and fsync it. At this time, server knows that all the data that's needed for this transaction to do crash recovery is in the redo log. It's not committed yet. Then the server takes an exclusive lock on the binary log. And all the transaction data in the statement format or in the row format when rows are changed is written to the binary log. After that, it's fsynced to the binary log to make sure it's persisted on the disk. And then the server raises the lock on the binary log. So once the data is in the binary log, the server would just go ahead and mark this transaction as committed. At this point, it's visible to any other transaction on the server that starts, will actually see the result of this commit. And then it sends ACK back to the client on step 9. Now, there's one sort of thing here. It still didn't commit the transaction to InnoDB in the storage engine on disk. It only committed in memory. And this is done because in this two-phase commit, so this is like, after sending the ACK, sometime asynchronously, it actually commits to the InnoDB. So the reason it does that is because the most important part of this sequence diagram is this fsync to the binary log. From MySQL's perspective, the data is committed if it's written to the binary log. And if it's not written to the binary log, the transaction is not committed. And the way it does that is actually during crash recovery. So, let's say a transaction was going through this sequence diagram or the steps and it crashed. Now, if it crashed before fsync, the transaction is not committed. If it crashed after fsync, the transaction is assumed to be committed. How does MySQL do that? So, when it comes back after a crash, it will go through the redo log. It may find some transactions that are committed, which have reached step 10. Now, all of those are fine to be committed because they're for sure in the binary log as well. Then it may find some transactions which didn't finish preparing. Now, all of those are uncommitted and we know they for sure never made it to the binary log either. Then it's left with a set of transactions that are prepared in InnoDB, but not committed in InnoDB. What it does with those transactions is for each transaction, it finds them in the binary log. If the transaction is also in the binary log, it rolls them forward. If the transaction is not in the binary log, it rolls them back. So at the end of crash recovery, you know for sure that your redo log, the transaction redo log, are consistent with the binary log. And this actually makes the crash recovery in MySQL a bit more complex and can take a long time because for every prepared transaction and not committed, you have to go find it in the binary log, just in the latest binary log, and do this roll forward or roll back. And sometimes roll back may be expensive because then you have to go to the undo log and find out all the data that you need to roll back in. One more thing that actually I want to point out in the sequence diagram is how expensive this operation is. The writing to redo log is fine because multiple transactions could be writing their changes to redo log and can be marked as prepared. But writing to binary log, because it's the logical log, transactions can't overlap each other, things like that. The server takes an exclusive lock on the binary log, writes the transaction data, and then fsyncs it. So it is kind of the bottleneck in this two-phase commit. The other thing is, let's say someone is running a very large transaction. They modified millions of rows, which would be fine. But when they actually commit the transaction, MySQL will mark it as prepared, then take a lock on the binary log, and has to write all those row changes to the binary log and then fsync it, which again can create a bottleneck if you have one large transaction. It may affect your other workload because now this transaction has a lock on the binary log, and is writing the data to the binary log. Yeah, so this is just a summary of the crash recovery that we talked about. Committed transactions are fine, unprepared are fine, but the prepared ones have to follow this logic. They're looked up in the binary log, rolled forward if they're there, rolled back if they're not there, and that's how MySQL's crash recovery works for a two-phase commit. So next I want to talk about group commit. So the thing I just mentioned was how expensive it is writing to a binary log. A transaction needs an exclusive lock, writes it data, fsyncs it, and releases the lock. So two-phase commit actually creates a big performance bottleneck in MySQL. So MySQL implemented this group commit to reduce the impact of two-phase commit. What group commit does is, if the first transaction that's prepared in InnoDB is ready to be committed, becomes the group commit leader. After it becomes the group commit leader, it waits for a certain amount of time, and that's configurable by a database administrator. And in that time, all the transactions that are also ready for commit to binary log would just join this leader thread. And after that, the leader thread will actually take a lock on the binary log, write the data, and commit it, and let all the other transactions know they're also committed to the binary log. So each transaction doesn't have to take a lock, write an fsync. One transaction does it for a group of transactions. Looking at the sequence diagram, those are numbered step 5, 6, and 7. That's the expensive part of the two-phase commit. So the first transaction that finished 5 is prepared in InnoDB would actually wait between 4 and 5. It will let a group of transactions to also be prepared. And then those transactions know that this is the leader transaction. It's going to take a lock on the binary log, write all of those transactions to the binary log and fsync, and send a notification saying all of those transactions are also committed. So this actually provides a big performance improvement on the earlier two-phase commit. But the thing I want to point out that the problem with large transaction is still there. If any of them is a very large transaction, the group commit for that transaction will take a long time, and the other transaction will still be waiting for that lock. So it doesn't solve that. There's another property about transactions that are in the same group commit. Like we know they were prepared together and they were committed to binary log together, which means all of those transactions actually don't fight for the same locks, and they don't have conflicting locks. And this is a property that can be also always used on the replica for parallel reply as well, that we'll see in the next slide. So I just talked about batching commits on the source. Before commit batching was implemented in MySQL, the source would be pretty slow. But with commit batching, it actually provided a significant throughput increase on the source. Now that's all good, but the problem is still my replica, right? If I have an HS solution with the source and a MySQL replica, if my source is very fast, it doesn't help me if my replica is still lagging. For example, if I have to fail over, I would have to wait for my replica to catch up and then fail over, which can cause a significant downtime. So parallel apply is something that MySQL implemented specifically to speed up the replica. And we will look at the different ways MySQL actually does parallel apply. So there are actually 3 or 4 types of parallel apply that MySQL supports. The first one is just database level, right? So let's say I have a MySQL server with tens or hundreds of databases. I can say, hey, apply transactions to all of these databases in parallel. But this is not a very common use case, right? No one has hundreds of very different databases on the same MySQL server. And you also have to make sure you don't have cross-database constraints, which actually MySQL supports. So this is a cool way to apply transactions in parallel, but it's actually not very useful in real world. Because in real world, we usually have, in production databases, we have 4 or 5 tables that are very busy instead of, distinct databases. So that's where the commit order parallel apply comes in. What commit order parallel apply does is, for every transaction, there's a commit window. Now the commit window is the timestamp when the commit started, a logical timestamp, and the timestamp when the commit ended. If two transactions have overlapping commit windows, which means they were committing at the same time, we know they don't have any conflicting locks. They're not modifying or touching the same rows. So what commit order does is tries to apply them on parallel. We discussed during group commit how the transactions in the same group commit are non-conflicting. And that was actually the first implementation of commit order. It was just saying if a bunch of transactions were in the same group commit, let's apply them parallel on the replica because we know they committed in parallel on the source. So they don't conflict with each other. But the group commit is not the only part of a commit, right? Before group commit, we are preparing the transaction in the source. After group commit, we're marking them as committed in the storage engine. So after the initial implementation, the definition of the commit window was extended to starting in the storage engine and finishing when the commit happened in the storage engine. So any transactions that have overlapping commit windows, MySQL actually can apply them in parallel on the replica because it knows they don't have any conflicting locks. So, after commit order, MySQL actually implemented a write set order parallel replication, which is even, I would say, a bit more advanced, can be even faster than commit order. In write set parallel replication, what MySQL is doing is on the source, keeping a track of which transaction modified which row. So let's say I have a write transaction that modified a bunch of rows. MySQL will write to the binary log, but it will also write the information, what was the most recent transaction that modified any of those rows. And this information will be present in the binary log. Now the replica can use this information to create a dependency graph of transactions, saying like which transaction touched the data that the transaction after this also modified. So it's sort of a dependency between two transactions. And using this dependency graph, it can apply those in parallel. There's also the write set session. It's just like write set, but with an extra guarantee that transactions from the same session wouldn't be reordered. Now I want to walk through these parallel apply techniques with some example. Here what I did was I created a table, PGConf, with an ID. And my second column is just a column called transaction. Don't confuse it with the actual transaction. I just did it so the examples are more readable, and my ID is the primary key. So here I have two users, one on the left side, one on the right side, and they ran a bunch of transactions. So the first user actually did a begin and a commit, which means it's part of one transaction. Inserted 4 rows with ID 1, 2, 3, 4, and the transaction, we name it as T1. And then it committed. After that, the first user updated row 1 and 2 in transaction T2. And then the second user updated row 3 and 4 and called it transaction T3. And they were doing it concurrently, so we assume that it was actually part of the same group commit. So these two transactions have overlapping commit windows. After that, user 1 updated row 1 with value T4 for the transaction, and user 2 updated row 2 with value T5. And again, those transactions were running concurrently, and they were part of the same group commit. And finally, the user 1 updated row 3 again with value T6, and user 2 updated row 4 with value T7, again running concurrently and part of the same group commit. So if MySQL is applying them as using commit order parallelization, we know that the transactions with overlapping commit windows can be applied in parallel. So this would be the dependency graph that MySQL will create on the replica. It knows T1 needs to go first because it's right, it committed first. And after that, T2 and T3 can go in any order because they were part of the same group commit. T4 and T5 need to wait for the last two because they don't have any overlapping commit windows. They started once T2 and T3 finish. And same T6 and T7, they started after T4 and T5 finish. So they can go in parallel with each other, but they have a dependency on the transactions before that. So that's the parallel replication using commit order. Now we'll look at the same example using write set, which can actually provide even faster replication in some cases. So the same transactions again, user 1 and user 2 inserted the 4 rows and then ran those updates that we talked about, part of the same group commit. Now I want to talk about the dependencies here, right? Now this T2 transaction T2 has a dependency on T1 because they're modifying rows 1 and 2. Transaction T3 has also dependency on T1 because they're both modifying rows 3 and 4. Transaction T4 actually has dependency just on T2, not on T3. Transaction T5 has also dependency on T2, not on T3, because they're not T3 and T5 are not modifying the same rows. And same, transaction T6 has a dependency on transaction T3, and T3 has a dependency on T1. T7 has a dependency on T3 as well, which has a dependency on T1. So MySQL is going to encode this dependency information in the binary log. What Replica will do is create this dependency graph. So T1 has to run first because it modified all the rows. After that, T2 and T3 can run in any order. T4 and T5 can run anytime after T2 in any order, and same for T6 and T7. So as we can see, this graph is not as deep as the commit order. So this is the way to speed up replication in MySQL if your workload can benefit from it. Now I just want to, in total I ran 7 transactions. Before MySQL only had a single threaded apply. So it will actually need to go through sort of 7 steps or commits to apply those transactions. And then using commit order, the same work can be done in 4 steps. So it was much faster. And then using write set, the same work can be done in actually just 3 steps. So MySQL can apply a lot of transactions in parallel using these parallelization techniques. Now, this is just an example of the binary log. I'm trying to show here that the information that is needed for parallelly applying transactions is all encoded in the binary log. I'm just outputting the binary log and emitting some of the information. Here, this information, last committed and sequence number. Sequence number refers to the current transaction, and last committed shows the dependency between the transaction. So what this is doing is, dependency transaction 2 and 3 have dependency on 1. Transaction 4 and 5 have dependency on 2. 6 has dependency on 3. 7 has dependency on 3. So this is all the information that MySQL encodes in binary log, which is used on the replica to generate that commit graph for write set parallel apply. Cool. That's the end of my presentation. I hope that folks working on logical replication found it useful. And we have 7 minutes to take any questions. Thank you. Yeah.
So the transaction sequence number that as part of the GTID, are they generated when transactions start or when they try to commit?
Yeah, they are generated when they actually are committing. Because transactions are in a specific order in the binary log in a growing sequence number. So, when you start a transaction, you don't know which order they're going to commit in. So when actually they go into the commit phase, that's when MySQL, after the prepare phase knows that if they're for sure going to commit, then it assigns each of them an increasing transaction ID.
So the sequence at which they are generated corresponds to the sequence at commit time? So is there here like a serialization of those transactions?
So it's actually part of the group commit, right? So at the group commit time, when they're getting committed to binary log, they're all being committed together. That's when MySQL will apply them these IDs.
So effectively, I might see, based on this, if I have selects on the replica, I might see intermediate results that do not correspond to any state that happened on the source.
If you have parallel apply?
Yes.
Yes. So if you have parallel apply, those GTIDs can show up out of order on the replica, right? MySQL actually has 2 settings. So the parallel apply that I talked about, so applying a transaction is a lot of work, is applying to the redo log and then committing it and then making it visible to the other transactions. So you can still use all of this parallel apply, but have a different setting that says, do all this work in parallel, but commit them in order. So you don't get as much throughput as you will get by committing them out of order, but you can still parallelize a lot of the apply work. So you can actually set both. You can say parallel apply, but externalize it or make them visible in the same commit order as the source. Or you can say parallel apply, but also make them visible out of the order, depending on what your application needs.
Thank you.
It may be out of scope for your talk, but I'm just wondering if MySQL has a similar way like Postgres replica copy, because in Postgres, before logical replication, we have an option to copy the table and get all the data of that table first, and then do the incremental replication after that.
Yeah.
So I'm just wondering, with MySQL, is there like a faster way to copy everything from the table before logical replication can start?
Yeah, I think the replication itself doesn't provide any way to copy the whole table, right? That has to be done outside. Like MySQL has a MySQL dump, which you can dump a table and load it, or depending on, there's some various backup solutions you can use to create a copy and restore it. But that has to be done outside the replication. There's no way in the replication to say copy all the data. Yeah, because replication never touches anything other than the binary log on the source. All it does, it copies the binary log, decodes it, and applies it.
Usually people have a snapshot and they know the GTID,
Yeah.
and then they just start replicating the binary logs from the snapshot's point in time. So that's what they use for that type of copy process.
Yeah, so if you have a snapshot, the system table with the GTID information would be in the snapshot. So when you restore it, you exactly know what GTID you need to start replication from.
So for the different parallel apply modes, and you mentioned also the commit ordering is something that you can still provide with some of that. What is the mode that most users of MySQL use? Like what trade-offs are most users willing to make with that stuff?
Yeah. It kind of depends on the workload, right? I think the thing that a user has to decide is whether they're okay with transactions being applied on the replica and visible out of order or not. So that's the main setting, but other than that, you can always use the right set parallelization, right? But
I guess what I'm asking is are most people okay with that, or is that something that a lot of people turn off?
I actually don't know.
Okay, I'm just curious. Yeah.
Right set is the default now.
Okay.
Right set in MySQL 8, some version is default, I believe. And you hit scaling limits with logical clock, so at some point you don't have a choice.
Okay.
And it's way better. And the idea of it is if you want something to be represented in your replica in the same order, then you include it in the same transaction, because it'll keep that order. If you don't care about it, most of the time means that it's different users touching different pieces of data. And so you're basically letting your clients decide what they want to see in the replica, because if they include it in the same transaction, then it will be represented in the replica in that exact way. And if it's not in the same transaction, then it won't be, potentially. But we're talking milliseconds, right? So,
I mean, is this something that's well understood by users, or is this something that surprises a
Definitely
lot
not.
of people? Okay.
not even close, no.
Okay, interesting.
You had a question.
Is there an upper limit on the GTID?
No, I don't. I don't know, but I don't
How is
think.
it encoded? Is it
Begin.
264? Is it 2128?
No, so the thing is, in the system table, you mean?
Yeah.
It's actually, so the thing is, if you're replicating, you may actually have different server UUIDs, right? So each server could have its own server UUID and GTID information, but like any server that it replicated from, and if that server replicated for something else, it's sort of a superset of all of those GTIDs. So it's actually a pretty big field. And as I saw in the system table, it's actually not recorded in the same row. It's stored as GTID intervals in different rows in the table.
We're talking about a max number for the transaction
Yes.
ID part?
Yeah.
Yeah, I'm not sure the exact type for that, but it is some sort of.
I'm just thinking if you got hyperscale, right? You go into trillions of GTIDs, you go into quadrillions of GTIDs.
Every time you fail over, it restarts.
It
So
restarts,
you have a new server ID starting at 1. And so if you had that problem, you could just fail over.
So there is a way in MySQL in resetting the GTID back to 1, but I actually haven't seen anyone hitting the limit.
Yeah, I haven't seen it either.
Yeah. Any other questions?
you have any recommended tools for monitoring the target server? Because like in general, a lot of things can go wrong, and then like when you're depending on the target, you need to know that kind of early on. So like, is there either monitoring tools or like things that the clients can use to detect that they're like,
Yeah, so there are a few things, right? There's just like MySQL commands. You can say show replica status. It will show you if the replica had any error, and it'll also show you how much is lagging based on the timestamp of the commits that is applied versus the last commit that saw in the binary log from the server. So you can use that and set up alarms on that. But GTIDs actually make it pretty easy, because if you're worried about any transaction, any data inconsistency, you can compare the GTIDs on the source and the replica and see if you're missing a transaction that you need to fix or things like that.
Also, most of the, like a lot of companies in the ecosystem use a tool called Orchestrator. It gives like visibility of replication chain and all the delays and stuff.
for some systems that prefer to like block writes from even happening if the secondary is down? Like it's an availability trade.
Oh yeah, so MySQL actually has a replication setting which is called the semi-synchronous, where you can make the source wait for a reply ACK from the target. I didn't cover it, but there's a way to set it up so you can enforce your replica has the transaction before you apply it.
It's not that scalable.
Yeah.
I had a question just about comparing to like Postgres. Do you work with Postgres a lot or at all?
No. I actually don't know a lot about Postgres.
Yeah, fair enough.
Perhaps someone in this room.
It's your question. Maybe somebody in the room knows.
Yeah, who in the room can I talk to after?
Depends about what, I guess.
Everything. No, just logical replication. Just questions.
Cool. I think we're out of time, but I'll be here at the conference. If anyone has any questions, always feel free to stop me. Cool. Thank you, everyone, for coming to the conference.